Um, what are you working on this week, Glenn?
Yesterday we started the chain rule and we just kept practicing that today.
Okay, so you're still on the chain rule.
Yeah.
Good. Why don't we spend some time going over some of these practice problems? That did you get this file? I mistakenly sent your sister's homework to a wrong email address, but I think I got yours correctly. Yours is Todd KS98, right?
Yeah.
Okay. So you got this okay? Did you have a look at any of them?
I looked at a few of them and they were pretty easy.
Okay, let me test you here. How about doing number 20?
Okay.
So we have y equals minus 5 over quantity t plus 3 cubed.
Okay.
What's the first thing you want to do here?
Bring the thing on the bottom to the top and
Yeah, let's write it without a denominator. There's no reason to use the quotient rule if you don't have to. Now what?
You first find the derivative of the outside, so it'd
Okay.
be
What's that?
negative.
Always start with that exponent, multiply it by the coefficient.
So it's 15, and then to the in parentheses t plus 3, and then outside the parentheses to the negative 4th power. And then after that you find the derivative of the inside.
Which is?
Just 1.
Okay, so that's our answer. Probably you want to not leave negative exponents in your answers. It's not a hard and fast rule, but it seems to be what everybody likes. So we would end up writing it like that. Either answer is probably acceptable. Okay. Give you one that incorporates the chain rule. Let's do 18. What's the first thing I'm going to do here?
Bring it to the top.
Tell me how to write it.
T, or in parentheses, t squared plus 3t minus 1, and then outside the parentheses to the negative 1 power.
Okay. Now what?
Then find the derivative of the outside, so negative 1, then in parentheses t squared plus 3t minus 1, and then to the negative 2 power outside the parentheses. Then find the derivative of the inside, which is 2t plus 3.
Okay. $22 looks kind of interesting. Let's have at that one here. So I've got G equals, well, I'm going to just start right off by getting rid of the radical sign. Now what?
So do the derivative of the outside first, so bring 1/2 out in front, and then 1 over t squared minus 2, and then to the negative 1/2 power, and then derivative of the inside, we're going to bring t squared minus 2 to the top, so we make it t squared minus 2 to the negative 1.
Notice we got a problem.
Yeah, we're gonna have to do the chain rule again, I guess.
Well, I'm not sure it's correct to do the chain rule twice here. Let's restart this whole thing by rewriting that inside this way in the first place.
Okay.
Because now, what can we do?
We can just do the chain rule.
Well, not the chain rule. What's the way to handle these exponents? We got double exponentiation going on.
So we multiply them.
Yes.
Yeah.
So the new exponent is minus 1/2. Now you're ready to take the derivative of the outside times the derivative of the inside.
So negative 1/2, then in parentheses t squared minus 2, and then outside the parentheses to the negative 3/2 power, and then inside it's just 2t.
Correct. And that's the best way to handle that. All right. You can never get too much practice taking derivatives. What's the derivative of 23? What's f prime?
Okay, so it'd be the product 2x, and then to the parentheses, or just write x minus 2 to the 4th again.
The way I call that is the quantity x minus 2 to the 4th. And that way you don't have to write begin paren, end paren.
Okay,
That's 2x times the quantity x minus 2 to the 4th. Okay, what's the rest of it?
And then plus 4x squared, and then quantity of x minus 2 cubed.
Hold on. Okay. What did you say, 4 or 4x?
4x squared.
Okay. The second part of this is this times the derivative of this. Right?
Yeah.
I would leave the hard part, the derivative, second. Always write that. Now there's no confusing. You took the derivative of that in the first step, and you're going to use that in the second step. So now what's the derivative of this part here?
4, quantity of x minus 2 cubed, and then that times 1.
Okay, we don't need to write. Okay, good. All right, let's go over and do some chain rules, I think. I mean, are there any other interesting looking problems here? This is going to be a huge quotient rule problem. Yeah, let's just start 30. There's a problem with some of these that involve the quotient rule. And that problem is that it's a great deal of algebra. It ends up being primarily an algebra problem. So if I had G equals this, how am I going to do this?
First, start off with finding the derivative of the outside.
Okay.
That's the 3 to the quantity of 3x squared minus 2 over 2x plus 3 cubed.
Squared, you mean?
Oh, yeah.
Okay.
And then find the derivative of the inside. So you have to do the quotient rule. So it would be 2x plus 3 times 6x minus 2 to the quantity of 3x squared minus 2 all over 2x plus 3 squared quantity.
And now you can kind of see that there's lots of simplification that can take place here. In other words, the denominators alone are going to turn into, you know what, we should go through this. Because, let me think for a second. If we distribute this, notice that we have a 2x plus 18x, so that's 20x, minus 6x squared plus 4. We have some 6x, or we're going to have some x squared here. Yeah, let's just go through the algebra here. This is a good thing to practice. You'd torture somebody if you made them do this all day long, but if you haven't done it once, you should go through it once. Okay? So, first of all, let's replace that with 20x. Okay? Let's replace this with 6x squared plus 4. With me?
Yeah.
Let's turn this thing into two fractions, the numerator squared and the denominator squared. And let's square the numerator. Ooh, boy, hold on a minute. Hold on. I was thinking we were going to be adding, and we're not. We're going to be multiplying the numerators. No point in doing that. Although, I think you can see that the denominator is going to end up being 2x plus 3 quantity squared also. So my new denominator, after I get done, is going to be 2x plus 3 to the 4th power. You see how that's going to happen?
Yeah.
My numerator is just going to be a long, complicated polynomial. Because after I FOIL that, I'm going to have some x to the 4ths, some x squareds, some numbers, and I'm going to have to multiply it by this trinomial. I'm going to have a 4 or 5 term polynomial. And I got to multiply everything by 3. So I wanted to do it hoping that we'd be able to do some major league cancellation. Because frequently in a problem like this, you'll be able to factor out something from the top that cancels with the bottom. So you'll have this enormously complex algebraic expression that, you know, cancels down to x plus 1 or something. And that happens a lot. We'll run into problems like that, I assure you. All right, let's go back and do some chain rule. Everything on the right is chain rule stuff. There were a couple of problems on the left that were chain rule. Yeah. I think you're pretty good on those chain rules. We're going to have to focus on these odd problems right here. Well, we won't have to. I could always look in my book and figure out what the others were. But what's the first one? What's the derivative of cosine of 3x?
Would it be negative sine from 3x times 3?
Correct. And I'm going to put the 3. I always write it at the end because you always do the derivative of the outside times the derivative of the inside. But after I'm done, I'm going to write it like that. Why? Because it's a little confusing if I were to write it like this. Even if I put a parentheses around that. Is that multiplying the 3x or is that multiplying the sine of 3x? Now, I can totally make it clear if I do that. And that's probably what I should do. That's probably the best way to do it. About this one?
That'd be 3 secant squared 4x times 4.
And 45?
So cosine pi, or 2 cosine pi x, or is that squared just to the angle?
First of all, this is not the same as this. This one means sine pi x times sine pi x. This one means you square the pi x and then you take the sine of it. Let's go over this, because this is my favorite way to really get somebody to figure out what the inside is. Let's do this one first. And then we'll do this one second.
Okay.
What's the inside?
The inside for this one is x.
Yeah, if I want to figure out what the inside is, here's what I'm going to do. I'm going to do some u substitution. What would I let u do? Well, if I let it equal to sine x, then I have y equal u squared, and I can figure out dy du. In other words, dy du would be 2u times du dx, and du dx is cosine x. So I'm going to multiply this, instead of by du dx, by cosine x. Go back in, substitute for u. I was using sine x. So by using u substitution, you can determine what to make the inside. Okay? Notice that if I made u x, I would be no better off. I still don't know how to I still don't know how to differentiate that because I haven't figured out what the inside is yet. I can't take the derivative of sine squared of u. Same reason I can't take it of sine squared of x. Okay? But I can take the derivative of u squared. So you have to figure out what to make the inside such that you'll be able to differentiate u. As long as I make it that, then this is going to turn into u squared. I know how to differentiate that easily. Now let's take the bottom situation. What's the inside here?
X squared.
Correct. Why? Because if I make x equal or u equal x squared, then what I'm doing is taking the derivative of the sine of u, which I know how to do. That's the derivative is cosine of u times du dx. Well, du dx, the derivative of the inside is 2x. So it's the cosine of x squared times 2x. This might be the most difficult one to figure out how to handle. This situation right here. There's going to be ones that are tough, but this gives everybody trouble. Figuring out what the outside is and what the inside is. Okay? So, in this problem that we're doing, number 45, the inside is that. So what's the derivative of the outside?
Cosine pi x squared.
Keep going. Times the derivative of the inside?
Pi.
2 pi x. 2 pi x. In other words, here's what our inside was. It wasn't just pi x. Notice that if we'd have made the inside pi x, we would have this problem, and we wouldn't know what to do. You don't know how to differentiate that. What we know how to differentiate is cosine of u. So we have to let u be pi x squared, so that when we take the derivative of that, that's the sine of u, which is the cosine of u. And now what is du dx, the derivative of the inside?
Pi.
Use the power rule. It's only a power rule problem.
2 pi x.
2 pi x. Okay, so I'm going to multiply.
So why do we keep the x?
Go ahead.
Why do we keep the x?
Because pi is just a number here. If I said u was equal to 3.14x squared.
Oh, okay.
Actually, you have a point. I am going to have an inside here. That's not du dx. Excuse me. That we took was the derivative of the outside. Well, we still have a derivative of the inside here.
Oh, yeah.
Pi. So there's your answer, 2 pi x pi. It's 2 pi squared. And the other way I could see that is if I turn that into so there's no confusion, that's the same as this. That's just a number. So du dx would be 2 times pi squared times x. So 2 pi squared x, and then you always go back and substitute for u. In other words, you don't ever want to give an answer like that. You want to turn it back into u of, well, that was pi x squared times 2 pi squared x. So that's the derivative of 45. That's a little tricky. That's a little tricky because figuring out what the inside should be is a little tricky there. Even trickier than my example. Okay. About 47. Sine of 2x cosine of 2x.
Okay. So cosine 2x times 2 times cosine 2x plus 2 cosine 2 cosine 2x times 2.
Oh, hold on. I get confused here because I never know which way the student's going. Okay, so you took the derivative of that times that. And now to do the reverse, let's take the derivative last, just so I always know where we're at. Okay, so the reverse is going to be this times the derivative of that, correct?
Yeah.
Well, let's write that part first. Now we got 3/4 of it done, and all we have to do is take the derivative of that.
So the negative sine 2x times 2.
And you're done. Now, the only thing you have to be a little careful with here, well, we're not quite done. We're going to do some combining here. But it's really easy, if you haven't immediately done it, to misread that. That almost looks like sine of 2x minus sine of 2x. And now I got parentheses around that, so you really shouldn't misread it. So let's condense all of this. Combine that, all of it. What's cosine of 2x times cosine of 2x?
Cosine 2x squared.
Cosine squared of 2x. There's a difference.
Yeah.
Okay. Plus what? Or actually,
minus,
it becomes minus, doesn't it? Too bad. If it was plus, we were going to be able to take a 1 out. But okay, so minus what?
2 sine squared 2x.
Good. And I could take the 2 and factor it out. And the only reason I might want to do that is because that is a trig identity. That is the double cosine angle identity. So I could replace that whole thing with cosine of 4x. I don't know how well you remember your trig, but cosine squared x minus sine squared x is equal to cosine of 2x.
Okay.
Now, I'm not sure you have to do this last step. No particular reason other than to make the answer a little shorter. If this turned out to be a plus like that, then we would definitely want to turn that into 1. In other words, that answer, cosine squared plus sine squared, is always equal to 1, no matter what the argument of each is. Whether it's 2x or x, it doesn't matter. It could be cosine squared of 15x plus sine squared of 15x, that's 1. So I would replace that whole thing. That whole thing is going to be equal to 2. 2 times 1. So sometimes you want to simplify, others you don't. When it was a minus, I'm not sure if it's a big advantage going cosine of 4x. Maybe. It's easier to differentiate, isn't it? Think about that. If somebody said, okay, now take the second derivative. Well, this is going to be much harder to take the second derivative of than 2 cosine of 4x. This piece of cake, take the derivative of. So there might be reason to turn that into cosine 4x. Just kind of depends on whether you need to take another derivative of it or not. Oops, that's f of x. What's f prime of x?
Would be sine x times negative cosecant squared x.
No, the derivative, oh, excuse me. Go ahead.
Minus, well, it'd become plus cosine x. Oh, no, wait, no, it wouldn't, It'd just be minus cosine x times cotangent x.
What's the denominator?
Oh, over sine squared x.
Correct. Sine squared x, not sine x squared. Right. Okay, now can we do anything with this? Again, I'm not sure how much they need you to simplify this. Notice that sine and cosecant are reciprocal of one another. So that's the same as 1 over sine squared of x. So this whole thing would become negative cosecant. And this, is it useful for us to spend time on trig or not?
I'm pretty good with that already.
Okay, good. You know how to, I'm sure you spent tons of time simplifying stuff like that.
Yeah.
And that's all you need to do. But I can certainly see that you can turn that into sine, some number of sine x. and this is cosine, and that's cosine over sine. So you could get sine, lots of sines in there, and you can do a lot of simplification, I'm sure. How about 51?
Would be 8 secant x sine or secant times cotangent.
Secant tangent.
Or yeah.
That's the derivative of secant of x. In other words, the inside is secant x. Okay, so we need to multiply the outside by the inside. The derivative of secant x is secant x tangent x. Okay. Let's do 53. '53 has two insides. I think this might be the first one we've looked at that has two insides.
So it'd be 1/2 sine cos, or yeah, 1/2 sine.
Sine of what?
To
Theta.
Times cosine 2 theta times 2.
Yeah, very good. That was the derivative of the outside. That was the derivative of the first inside. That was the derivative of the second inside. Now, yeah, some of these are going to get really hard to figure out what is the first inside and what is the second inside. But let's just keep going. When we encounter one, we'll figure it out.
So it'd be 6 secant squared, or secant pi times t minus 1 times secant cotangent.
Not secant cotangent, secant tangent. But it's secant of pi t minus 1 times tangent of pi t minus 1. So there's the derivative of the outside. There's the derivative of the inside, but there's another inside.
So times pi.
I'm thinking for a moment here. So it's just multiplied by 1 pi. Let me go through this problem a different way so that I'm positive. I know what I'm doing. Okay?
Okay.
And the way that is using U substitution. I'm going to leave everything up there that I wrote, but we're going to check it by using U substitution. Okay? The first U that I'm going to use is secant of pi t minus 1. Because now I will have y equals 3 times u squared. And I can use a simple power rule on that. That's 6u. So y prime would be 6u times du dt. Well, let's figure out what du dt is. Du dt is secant pi t minus 1 times tangent of pi t minus 1 times the derivative of the inside. So it's just 1 pi, like that. So we did it correctly. I was a little confused because by the time I wrote all of that, now I'm thinking, do I need to multiply it by the derivatives of both insides? In other words, do I need to multiply it by pi for that one and pi for that one? And the answer is no. And the only way I could really prove it to myself was to go through u substitution. And always remember that the very first you substitute, you can find y prime, but what you have found is not dy dt, you have found dy du. That's okay, because if I multiply dy du times du dt, I get what I'm looking for, which is dy dt. That's where the chain rule comes from. Okay, so all I have to do is figure out dy du, knowing that I can do that. I know how to do that. And then going over here and figuring out what is du dt. And that only requires one application of the chain rule. So I get everything right. And then I, of course, got to go back and substitute for u. This has now become secant of pi t minus 1. So I'm going to have a lot of those. I'm going to end up with a secant squared of pi t minus 1 by the time I'm done here. All right. And we're on a roll. Let's do 57. What does y prime equal?
Well, would be 1 half x the negative plus 1 half x.
Hold on. Can't use the power rule for this part. Let's ignore that so we don't waste space. That was just a distractor. Let's figure out how to differentiate that. In other words, let's differentiate this. This is the one that is tough because this is the one different. In other words, this has a different inside than if that 2 was right here. What's the inside going to be?
2x squared.
Yes, 2x quantity squared. And just so we don't accidentally forget, let's make that 4x squared, because that's what it is. So when I go to find du dx, I won't make a mistake. Although I could apply the chain rule twice to get that 4x or 8x. We'll do that. We'll apply the chain rule twice. We'll just leave it like this. Okay, so now take the derivative of the outside.
1/4 cosine 2x squared.
And the derivative of the inside.
So 2 times 2x times 2.
And there's, well, I guess your final answer. I could change this to cosine. Here, let's change it to this. Let's put the polynomial in front. So we end up with 2x times cosine of 2x squared. Or I could do away with the parentheses and write 4x squared. But that's going to be my final answer. If you had e to the x yet? Derivative of e to the x? No or yes?
Yeah.
Okay, so what's the derivative of this?
E to the 3 to the x.
E to
Or
the
e to the 3x.
Times?
Times 3.
Uh-huh. In other words, that's the inside. So the derivative of the outside is same thing you started with, times the derivative of the inside. And how did I know what to make? In this case, it's pretty obvious what the inside is. There can only be one inside. But I'm going to do that because now y is equal to e to the u. And I know what that derivative, I know what dy du is. That's e to the u times du dx, which is 3. So I end up with 3e to the 3x. The only ones that are really, the only ones I find difficult at all to figure out the derivative, or to figure out the inside, is those trig functions. In other words, the only one I can even think of that's a problem is the difference between this and this. I can't think of another case where you would really have difficulty figuring out what the first inside was. Might be a little tough on a problem like that, but not really. Once you've figured out that the inside is sine x for that, and that the inside is x squared for that, then use that knowledge whenever you run into trig functions. Here, let me do this. Okay. I want to give you some homework, and the homework I'm going to give you is going to be the even numbered questions on this page. Okay? Since my photograph didn't show those, and we've been working on the odd functions during this session, in the next 11 minutes I'm going to go down and do some of these down here. So I think it's probably appropriate for you to do some homework on the chain rule for this coming week. I wouldn't be surprised if you spend most of the week still working on the chain rule. It can be a little bit difficult to understand for some people. Does that sound okay with you? So these even questions over here, I will send you a file that has a picture of those.
Okay.
And that's fine. That's good enough practice for the chain rule. But in the meantime, let's go down and look at 59. And the instructions on 59 say, evaluate the derivative of the function at the given point. And in this case, the given point is 2, 4. So the first step, S prime of t.
Would be 1/2 c squared, or separated c squared plus 2t plus to the negative 1/2 power.
Oh, plus 8, right?
Yeah.
Okay, I didn't hear that. Audio might have just cut out. Okay.
That times 2t, the quantity of 2t plus 2.
Now evaluate that at the point 2 comma 4.
So would you just plug in 2 for t?
Yes. In other words, what they're saying is, what is S prime of 2? We don't need the 4. Once you get to implicit differentiation, you will need the 4. When you get to implicit differentiation, you end up with y prime being a function of both x and y. Okay? For this we're still explicitly differentiating. The only evaluation they're ever going to want us to make is when the one variable is equal to that. So that's always going to be the key variable. So evaluate this at t equal 2.
So it equals 6 over 4.
Whatever this comes out to be. Again, this is just algebra. I'm assuming you know how to do this.
Yeah.
Okay. Oh, I see. That's 16, huh? Yeah. It's not 6 over 4. Don't forget this 1/2. In other words, the square root of that is 4. So it's really going to be 3 over 4, isn't it?
Oh, yeah.
Okay. What's coming up next? Rather than going through stuff that I know you know, let me give you a head start on implicit differentiation. Because you may get done with the chain rule sometime this week, and they'll want you to learn. In my book, the very next thing that's coming is implicit differentiation. Well, let's talk about that. If sometimes I'll have a function, if I have a function y equals, then it's pretty easy to explicitly differentiate it. It doesn't matter how complicated I am over there. I can use a combination of the power rule, product rule, quotient rule, and chain rule to come up with y prime. But what if I had something like this? Now, I can't solve for y. If I could solve for y, I would, and I would explicitly differentiate it. But I can't. But what I can do is implicitly differentiate both sides. Okay? In other words, I have an equation here, and what I'm allowed to do is differentiate the left side with respect to x, and differentiate the right side with respect to x. Differentiation and integration is just like anything else in algebra. Whatever you can think of to do to one side of the equation, as long as you do it to the other side, you're fine. Well, how do I differentiate this expression with respect to x? Well, I've got to take the derivative of the outside times dy dx. In other words, this first term, because it's a variable that isn't x, I need to differentiate it and follow it with a dy dx. In other words, whenever I encounter a variable that is not x, I follow it with a d that variable over dx. Okay? So I've differentiated that term. Now let's go to this term. I got to use the product rule. So I'm going to do x times the derivative of y. Well, the derivative of y is 1, but once again, y is not x, so I have to follow it with a dy dx. Using the product rule, plus the derivative of x, well, x is x, so I can just take the derivative of x, which is 1, and I don't have to follow that with a dx dx. I guess I could, because dx dx is also 1. But I do have to follow it with y. And notice I do not follow that y with a dy dx, because I didn't differentiate y. The second part of that product rule, I was only differentiating x, right? It's the derivative of x times y. Well, if you're not differentiating y, you don't need to follow it with a dy dx. And the other side of this equation is 0. With me?
Yeah.
Now, to solve for dy dx, we collect all terms that have a dy dx in them and put them on one side of the equation. We put anything that has not a dy dx in it on the other side. So all I'm going to do is move this y to the other side of the equation, make it a minus y. Now I'm still trying to solve for dy dx. This is the key step that a lot of people have difficulty with. You got to factor out dy dx. You're left with 2y plus x. Now notice that dy dx is going to be equal to y divided by 2y plus x. In other words, my derivative is a function of x and y. And so if they wanted me to evaluate this derivative at some point, it would be very useful. If they want me to evaluate this at the point 2, 4, then I plug in 2 for x and 4 for y. So that would be 4 over 8 plus 2, 10. So that would be 2/5 is the derivative at that point. And
What happened?
I'm sorry, what?
What happened to the negative sign?
I dropped it. Thank you. Yeah, when I simplified it, I erased it or didn't see it, one or the other. But thank you. Okay? And this is so valuable because we started with a function that we really couldn't solve for y. Okay? Now, the other place where it's really valuable is when you get to related rates. And, we don't have enough time for me to get to related rates, I guess. But sometimes, I can say these few things. Sometimes I'm going to differentiate both sides, not with respect to one of the variables, but with respect to a variable that's not even in there, like time. In other words, in this case, I'm going to differentiate everything with respect to t. So every variable I run into, I got to follow with a d that variable dt. So this becomes 2y dy dt plus x times dy dt plus dx dt times y equals 0. And now notice you have a dy dt, you have a dy dt, and you have a dx dt. So when you differentiate an equation with respect to a variable that isn't in there, then this will make a lot more sense. Why this is valuable to you is that when you get to related rates, this is what you're dealing with. We have a bunch of related rates. That's the change in y, that's the change in x. But for the moment, you have to master implicit differentiation. But implicit differentiation is really easy if you just follow that rule. That whenever you encounter a variable that is not the variable of the denominator, follow it with a dx dt. If it's x and you run into an x, you don't have to follow it. You can just explicitly differentiate it. But if it's anything that is not one of those variables, you have to do that. You'll catch on pretty quick once you cover it in class. I think you'll be there. Okay, that's a good spot to end on. And like I said, I'll be sending you an email that has these even problems on it.
Okay.
Okay? Saad, I will talk to you next week. Have a good week.
Okay, you too.
Bye-bye.